Hi all, this is Mr. Yeager again, doing one more follow-up with linearization, just so you kind of hopefully get the idea. This is one of the worksheets that you're working on to kind of get the idea of how to look at different equations that we'll be using throughout the year, what to put on the x-axis and the y-axis, and then find what would the slope equal if you graph it appropriately. So if I look at the first one, what we're saying here, I'm going to do just 5 problems and then one more linearization example. What we're looking at here is this is your standard velocity formula related to acceleration. What they're saying in the second column is you have data for v and t. V on the left side and t on the right. The whole idea is you're trying to line everything up with this equation, y equals mx plus b. If you graph y and x appropriately, you will get a straight line, and then you'll have m left over. There is a couple b's on this, the y-intercepts, but we'll talk about those when we get to them. So for the first set, basically all I do is I write over it. Y equals, it's going to be mx over here plus b in the middle. Why am I putting it over there? That's because, one, mx is 2 variables. I must have 2 things that I'm measuring with m and x. So the only things that are together is a and t. The other reason I'm doing that is, obviously y is on the left, so I'm lining that up with v. So velocity is going to be on my vertical axis. And then I can line x up with t. T is going to be on my horizontal axis. Do I need to square anything like I did in that one problem? No, because there's nothing squared in this formula. There are no squares. So what do I have left? Well, whatever is in front of my x variable is my slope. On this one, the slope is equal to a. So if you actually graph the velocity versus time, the slope would be a. We don't need to do anything else with it. Once I find the slope, it's a. This problem, it does have a y-intercept, v0, what's called the initial speed. Could it be 0? Sure. It could be anything, though. It could start somewhere above or even below the x-axis. Okay, and again, we'll learn about that more later. The second one, this is the exact one we did in the Joker problem. Y equals mx plus b. So again, I'll go ahead and label it. We already know x is on my vertical axis, and I know x0 is my y-intercept. Again, I don't care that you might not understand what the symbols mean, but we can definitely line everything up. X, I'm measuring t, but this time x must be t squared. So what I would do with all my t's is I square them all and graph t squared. What is then left for m? 1/2 a. So that's the example we did. Number 3. I have data for a and f. So y equals m times x. This one's pretty easy. Everything lines up really nicely. F is on my y-axis, vertical axis. A is on my x-axis. I'm using a because that's the data that I have, which means m is my slope, and there is no y-intercept. Okay, there's no plus. What about if I do this is kinetic energy equals 1/2 mass times velocity squared. I have kinetic energy and velocity, so y equals m times x. What's on my vertical axis? K. All right. What's on my x-axis? Is it just v? No. I'd use also those velocities, and I'd square them all and then graph it. That would mean my slope would be 1/2 m. Would be half the mass. So if I wanted to solve for mass, I'd get the slope and then multiply it by 2, okay, to get the mass. All right. What about this last one here? I have u and y. This is gravitational potential energy equals mass times gravity, the acceleration due to gravity times the height. So y equals m times x. Y would be u. X would be the y, which I don't need to do anything to, so I can just graph the 2. That would give me a slope that is m times g. So the slope is a product of mass times the acceleration due to gravity, with, again, no slope. All right? So that, again, you have a lot more to try to practice with. If you have questions on those, please make sure you let me know. Let's look at one more problem that is basically you're doing as well for practice. Okay? It is with Newton's gravitational law, okay? Where you can see on this, you're given this particular equation, F equals gmm over r squared. Okay? So you are given data for F and R. If you graph it, you'll get something like this. It looks pretty straight, but then it actually curves out. It gets very flat on the bottom. So this is again a curve, which we knew was going to happen because the formula is f equals gmm over r squared. There's a square value of something you're trying to graph. That will make it a curve. So what do we have to do? Okay, this one I'm going to be a little quicker. You can go back and check all the work. I'm going to graph. Actually, this is a little bit harder for people to see, so I'll take my time. I'm going to graph y equals m times x. Force I'll keep the same. I'm not going to change the y-axis. It's force. But I have to do something to r. I'm going to do 1 over r squared. Why is that? Because this gmm over r squared is the same thing as saying gmm times 1 over r squared. Sometimes that helps people see what's going on. M times x. So what I'd have to do is I'd have to take all of those r's and do 1 over r squared and get the whole values. So in this particular column, dang it, I would do 1 over r squared all the way down with all the values. I would then graph f versus x, 1 over r squared, and then you can see my data comes out to a much straighter line. I would then obviously do a best fit line. Best fit lines is actually another mistake. Don't have to go through 0. Obviously we're expecting them to, but they don't have to, okay? So for this one, I'm going to make it like that. Not perfect, but basically you go ahead and line up a ruler and make it. What would the slope equal? The slope would equal gmm. So it's actually a product of a lot of variables. I think in the problem set that's on that page that I'm showing on this, I think it tells you, yeah, graph your data, and I think it then goes on and says, well, what if one of the masses is this? What would be the other mass? Yep. Okay. So the idea would be, if you know what G is a constant, so that would be given to you, and you get one of the m's, how could you solve for the other mass? I would simply divide them both over to the other side, because you have the slope. This m, I know it's confusing, this is the slope m. It equals gravitational constant times mass times mass. If I divide this over to the other side, I can solve for the final mass that's creating this graph. Help me to create this graph. All right? So that's just another example. We can, obviously the 1 over r squared scares some people. You can do whatever you need to the data to get to match it up with the equation you're trying to use, and then solve for the slope. All right, that's it. Thank you.